Say good afternoon. Welcome back to another physics video, and I'm happy to tell you that we're pretty much done with discussing vectors, at least in the mathematical sense. Now, don't worry, don't fret, they're going to come back. It's just going to be in a more physical based sense when we're talking about positions or velocities, etc., accelerations, etc. So not to fear, they will come back. So we're moving on actually to chapter 2, and in chapter 2, since you've probably already looked at it, we're starting to deal with ideas of motion. You might say, well, this is kind of boring, but don't forget everything that we've dealt with, or everything in the physics world, is based off of these ideas about motion. And so it's really important to get a firm understanding of what we're talking about when we're doing these kind of things. Maybe I would also go into a nature of science discussion and say, this kind of relates an observable to inferences. So as we start progressing through the material, I'll mention this again, but it's always good to ask yourself, what am I actually observing? And based off of those observations, what can I infer? To give you an example, your brain is not instantaneously fast. Your eyes record data, and then your brain paces them together. In fact, this is how things like cartoons work. Or you could just say television in general. TV is not giving you a nice video image. What it does is it presents a series of still images where there's small changes, and your brain actually interprets that as motion. So even your brain, your eyes are working off of this idea about recording individual positions and then extrapolating or inferring the motion between those. So that's why we're starting here. And actually Newton had this nice insight that it wasn't particularly the position of an object that was important. It wasn't the velocity of the object that was important. It was actually the acceleration. So we have to work our way up. What does it mean to have a velocity? What does it mean to have an acceleration? So we're going to start here. So let's go ahead and get rid of that. Here we go. So we're dealing with motion. And maybe the first thing I should start off with is some notation here, And here's our first foray into Greek letters. And in particular, the one that we're dealing with today is the capital delta. So I'll put delta here. Delta. If I could spell. Let's try that again. So we're going to deal with the capital Greek letter delta. Okay. And when you see this has a particular meaning in physics, and the meaning would be a change in. Okay, so anytime you see delta quantity, it's a change in that quantity. For example, you could, although I don't see this, but you could say your bank account undergoes a delta dollar sign. There's change in the amount of money in your bank account. Now, this is not usually, you don't see this in physics, but you could say something like a change in the x position of an object, or the change in the speed of an object. So that's where we'll more likely see it. And for those of you, since we're in 162, you will be seeing this in calculus as well. In fact, this is the notation, or this is how you first introduce those painful ideas about derivatives. You first start talking about finite changes, and then you just simply start thinking about the limit as those finite changes get really small. So you'll see this again in our book and also in math class. So it's a change in. Now, how you actually calculate this value, how it's calculated, I'll say delta, I will define that as being the final value minus the initial value. Okay. That's how we actually calculate the change. It's what is it at the end, what was it at the beginning, the difference between those two must be the change. And it can be, note, if the final is larger than the initial, the change is positive, it increases. If the final is less than the initial, you get a decrease and a negative. So this takes care of signs, if you will. So if you end up with a negative sign, you know you ended up with less than what you started out with. Okay. So that's where we'll first start. Okay. Now off to the nitty-gritty details. And the first thing that we'll start off with is motion, and I'll be even more specific. I'll say 1D, one dimension. Okay. So we're going with this bottom-up approach. In other words, we're going to try to get you familiar with the one-dimensional motion and how to treat that, and then we're going to move our way up into three-dimensional motion. I will tell you right now, it pays to actually learn this. Of course, that's not a surprise. But the trick is that if you can do 1D motion and you can do it really well, then you should not have too much problems with 3D motion. And this comes back to the idea from the last couple of videos or a couple of videos ago. It comes back to the idea that your X direction, your Y direction, and your Z direction are perpendicular to each other. In other words, motion in the X direction does not change my Y coordinates, or motion in the Y direction does not change my Z or X components. They're independent of each other. So if you understand 1D motion, then going to 3D motion is not a big issue. It's three independent directions. You can treat those as if it was 1D motion in the X direction, 1D motion in the Y direction, 1D motion in the Z direction. And you'll hopefully see that. The only difference, really, the difficulty is instead of having one equation that you're trying to use, you might have three. Okay, so that's fair enough, but that's a mathematical problem, not a physical issue. So that's some motivation, hopefully, to actually get really familiar with this 1D motion. And so we will, without loss of generality, we will just take the X direction right now. Well, let's consider the X direction. And if you prefer, you say, well, I want to do the Y direction, that's fine. This is just some sort of stand-in variable. Well, that's all I have to say about position. That's actually going to be our first observable, and we're going to build up from there. So the next two ideas that we need to sit and talk about are velocity and speed. And now, usually in everyday vernacular, we'd probably interchange those two and not really think about the difference. But from a physics sense, we have to be very careful. These are actually two different quantities. So we'll start off with velocity, and I'll be even more specific. Since we're dealing with motion in the X direction, I'll say 1D motion in the X direction, I should say that I will give you how to calculate the X component of the average velocity. So I will do this as, I'll say V average to remind myself that we're dealing with an average velocity, and then I'll put a subscript X. So the X component of the average velocity. So you say, well, wait a minute, that means that the average velocity should have a Y component, a Z component. Yes, indeed, velocity is a vector. So there's already the transition into some 3D motion. Now, the X component of the average velocity, that is simply equal to the change in the position over change in time. And there we go. We are all set and done. You know, you might ask yourself, and rightly so, how does that differ from speed? So I'll put over here, for lack of a better notation, I'll just put speed for right now. You say, well, what's speed? How do we calculate that? And I'll put it in words first. I'll say, the speed of an object is the total distance traveled divided by total time. You say, well, wait a minute. How does the speed and the X component of the average velocity actually differ? And I'll say this. If your object is moving in a straight line and does not change direction, then you're going to end up with the same value for both of these. Your x component of the average velocity is going to be equal to your speed. But you notice I put a lot of caveats on there. I said, wait a minute. So first of all, travel in straight line, or maybe this is probably even more general, doesn't change direction. Okay. So for example, you say, well, how does that come in? Say, for example, I have an object that starts out, say, here. It moves to some distance and then turns around and loops back. And so when I first look at it, it's right here. This is the initial position. And when I look at it again, here is the final position. And so if I were actually calculating the average speed in the x direction, here's my final position, here's my initial. This distance from here to here, that would be my delta x, right? That's my change, final minus initial. My final position's here, my initial position's here. That's my delta x. And I apologize, I drew those offset so that you could actually see, what was going on. Now, if I were actually calculating the speed, you notice that my total distance traveled is not this distance delta x. My total distance traveled is this whole stretch from here, stopping, turning around, and coming back to right here. That would be my total distance traveled. So my total distance, d, is much greater. I'll say the total distance traveled, d, is much greater than delta x. And so we're going to find that the speed of an object can be much greater than the average velocity in the x direction. In fact, if it's traveling in a straight line and doesn't change direction, then these two should be exactly equal. Anything else than that, and you're going to end up with the speed being greater than the average velocity in the x direction. So there's the difference there, and we need to be careful. More often than not, we're going to be talking about velocities. Okay? And if this condition is met, again, traveling in a straight line doesn't change direction, we'll actually find that the speed is equal to the magnitude of the velocity. And this is often where you see it most often interchanged. So I might be saying the speed of an object. Right away, I'm inferring that the object is traveling in a straight line, doesn't change direction. And I'll say the speed is the magnitude of the velocity. Or we'll be dealing with velocity vectors, and I'll say, oh yeah, the speed. Okay, so that's usually where we'll see that come into play. If we're traveling in a straight line and don't change direction, the speed is equal to the magnitude of the velocity. So now I've got a different question for you. And this is more along the lines of I want to present some different ways of presenting motion. And here's one of them. So let's go ahead and I'll put that on here. In fact, I'm going to scale that up just a little bit so you can see it a little more. And this is what I'm going to refer to as a strobe diagram. Okay? Let me explain what's going on here. So we have an object that's moving. So that would be the ball here. And pretend it's moving in a dark room. And every so often, periodically, at regular intervals, so delta t is fixed. Some delta t, some regular interval, delta t, a flash goes off that allows you to actually see the position of the object. So the first flash, position of the object at A, second flash, position of the object at B, third flash, fourth flash, fifth flash. So this is what I refer to as a strobe diagram. It's conveying the position of an object at regular time intervals. And so here's the question I have for you. Between which pair of consecutive points is the average velocity in the x direction the largest? So go ahead, pause the video real fast, get an idea about that. All right. Say, okay, well, I know what the average, how to do the average velocity in the x direction. That's a change in position over a change in time. Since in the strobe diagram, the time intervals are all the same. The time interval between A and B is the same as the time interval from B to C, time interval from C to D, et cetera, et cetera. So in order to find the highest average velocity, I need to find the largest change in position between two strobe flashes. You say, okay, well, I can do that. Aha, it's right here. This is the largest change in position from D to E. Therefore, the highest average speed, say the highest average speed is between positions D and E. Largest. Okay. Cool. So the next question I have for you is this. Between which two pairs of points is the speed of the ball the highest? So I'll give you a second. Go ahead, pause the video, hack that out. Okay. And say, okay, Greg's being pretty facetious here because I would argue you can't tell between which two positions the speed of the ball is the highest. Because let's think about this again. What do you observe? You observe the ball at position A and then at position B. But there's nothing that says that the ball traveled in a straight line from A to B. Okay? You've inferred that. If you were thinking that way, that's a common idea, but you've inferred that. You said, okay, it's traveling in a straight line at constant speed. And I've already warned you that's not necessarily the case. You don't know. Say, for example, the strobe flash goes off and the ball bounces, and then it happens, just so happens, to strobe flash when the ball's on the floor again. And then maybe it bounces again, and then it bounces again, and then it bounces again. That could be going on. You don't know. And so it's impossible for you to actually figure out what the total distance traveled is. Okay? So that's... You can't actually say which point it's the highest. Maybe it doesn't have to bounce at all. Maybe you're seeing the ball on the ground and it has some sort of backspin on it or something. So some goofy flubber type ball where it starts at A, it flashes, it goes all the way out to E and then comes back to B during the second flash. And then maybe the next flash, it goes all the way out to E and then goes back to C. And then, so I think I'm beating a dead horse here. I think you see that it's not really possible for you to answer this question. Based on the strobe diagram, you can't say anything about which position has the highest speed. You can only say something about which pairs of points have the highest average velocity. So the next thing that I would like to use the strobe diagram for is trying to connect a strobe diagram to a graph. So here we've got a new strobe diagram down, and let's say that, for example, the time interval between flashes is 1 second. So I want you to go ahead and actually draw out a diagram. What will the plot of, say, x in meters versus time look like? Oops. Time in seconds. So go ahead, take a moment, figure out what that would look like, draw it out. Okay, if you're not done yet, go ahead and pause the video and you can pick it back up when you need to. So here I look and I say, okay, well, I've got a distance and it's 1 meter. And so at time equals 0, I've got 0. And at time equals 1 second, I've got 1, and 2, I'm at 2 meters, and 3, I'm at 3 meters, and 4, I'm at 4 meters. Okay, and you say, okay, well, that's, I understand what's going on there. And so you know that to get to here, there's been 4 flashes, 1, 2, 3, 4. So 4 flashes. Each flash is 1 second, so it must be 4 seconds, and it's at 4 meters. So there we are. Now we have to be careful here. Okay, if I said the thing I want you to be careful of now is that maybe some of you might be tempted to actually draw a line in connecting all those points. Say you drew a line through like that. Okay? And I say, wait a minute. Say, wait a minute, we just talked about this. How do I know that something goofy isn't happening between the flashes? Say, for example, maybe the ball's bouncing between the flashes. Okay? How do you know that that's not happening? And the short answer is you don't. You don't know that it could be bouncing. You don't know for sure. And so drawing this line through the data points, that's a no-no. You can't do that. Drawing this line in says that you made those observations and you haven't. So this is what the graph looks like. This is all that we can do right now. But then here comes my next question to you. And the question is this: how can you get a better graph? How can you gain confidence that the ball is not bouncing, for example? Okay, pause it, you think about it. And one of the things that you could say is, well, instead of spending, say, 1 second between flashes, maybe that's a bad time interval. Let's do something else. Let's say I do half a second, 0.5 seconds. And I agree, that's an excellent idea. Now, let's say after 0.5 seconds, each flash, now you see the ball right here. Okay? Maybe halfway in between. So that gives you additional data points that you can put on your graph. You say, aha, now I can put a line through. You say, oh, no. How do you know that the ball's not doing this instead? Maybe it's now just bouncing more often than what you thought it was. That could be a possibility. So you say, okay, I know exactly how to fix this. What I'm going to do is I'm going to take this thing and make it really, really small. Really, really small. Say you make it like 0.001 seconds. And I agree, that's the best way to do it, okay? So when you see for these motion graphs, when you see these motion graphs and you see a line drawn through, something like this, what you really need to be thinking about is not that they took it at, I mean, the limit is instantaneous, and you know that you can't do that. What we're thinking of is that your time interval is going to 0. In other words, it's really, really small. Really, really small. And that's kind of what allows you to put all of these extra lines in. Okay? And that's, again, that's a bit of a conceptualization, but that helps us actually gain confidence, or it helps us to conceptualize what's going on here. So now the other interesting thing, of course, is that this idea, okay, getting an accurate picture of the motion of the ball is what led Newton to introduce the idea of calculus. So you'll see this, but we've already defined the average velocity in the x direction. We've defined that, we've given that as delta x over delta t. Okay? Now, in the limit, so what we'll say, the limit as delta t goes to 0 of delta x over delta t. Okay, so if we take this limit. We want delta t to go closer and closer to 0 to get a better and better picture of what's going on. Or if we want our strobe flashes to happen at really quick time intervals so that we know really well the position of the ball. So instead of calling this the average speed, we actually define that as the instantaneous speed. So if you could take those two quick pictures, click, click, really fast, you'd basically know at that very instant when the picture was taken, you would know the instantaneous speed. Okay? And that's the difference between the average speed and the instantaneous. It's only a matter of how quickly are the pictures being taken. Okay? Incidentally, this notation is somewhat cumbersome, and you know that physicists are outright lazy. You know who's even lazier? Mathematicians. They don't like having to write this quantity all the time. So they come up with some special notation. Rather than writing the limit as delta t goes to 0 of delta x over delta t, they just simply write it as dx dt. And they call that the instantaneous speed or instantaneous velocity. I should be more careful. This is the instantaneous velocity in the x direction. Okay. So this is just a small notation change. We're lazy. We don't want to have to write this every time, so we come up with different notation. And this is, you've probably heard this term already. This is called the derivative. If you have not seen this yet, you will soon. But just please note that it's just a notation issue. You're talking about taking these flashes and having them really close together so that you know precisely what the position of the object is. Okay. Good. So the other, say, okay, well, we've got position. I've given you some definitions and average velocities and instantaneous velocities. The only other song and dance that we need to do is talking about acceleration. And as I've hinted at before, so acceleration. And as I've hinted at before, acceleration is really as far as we really need to go in this game of motion. We observe positions, we can infer velocities, and from the velocities we can get accelerations. Now the idea that I think of here is, imagine for a moment, you can do a thought experiment, or maybe we can do it here on, even better, we should just do that here on the desk. Okay, so let's go at this. I've got a little bit of a setup, just a screen for us. I've got a ball here. Oops, yes, so you can see it. And all we're doing is our simple experiment. Rolling the ball. Let's get that. Rolling the ball behind the screen. Now, of course, you say, okay, that's everything I expected, and we'll sit down and talk about why that is. But let's go ahead and do it again. And now, the question is, how do you know something happened? And I would argue what you're actually observing is you're actually saying, hey, there is a change in velocity. Okay? If nothing's going on, you observe the velocity of the ball before it goes behind the screen, and you can kind of extrapolate, okay, if it's moving at that velocity, it'll come out from the other side. And that's the natural thing. You see it go in on one side, you expect it to come out on the other. And it's the fact that it stops, right? It violates that expectation. Then you say, wait a minute, something happened. Greg must have stopped it somehow. So what's the interesting thing is the change in velocity. And that's leading into this new quantity called acceleration. We use the letter A. Acceleration, again, is a vector. Okay, so it has three components. Since we're doing in 1D motion, we'll talk about the acceleration in just the x direction for the moment. And we'll play the same song and dance. The acceleration in the x direction is just defined as the change, I gotta be careful here, of the x component of the velocity per unit time, delta t. And already you can see I'm getting a bit lazy here. Or maybe I should say this is the acceleration in the x direction, and it's the average. Okay. If I want the instantaneous, you already know what to do. Take the limit as delta t goes to 0. If I want to get a better idea about what the average acceleration is, or excuse me, if I want to get a more precise measurement of the average acceleration, I should have the strobe flashes happening faster. That means that delta t goes down. And so I would get an instantaneous would equal dvx dt. Okay. So as long as you're comfortable with the relationship between the average speed in the x direction, which is delta x over t, as long as you're comfortable with this relationship, somehow my square got, as long as you're comfortable with this relationship, then this is the exact same relationship. It's just different variables. So instead of the relationship between x and the average speed is the same relationship between the average speed and the average acceleration. Okay. So that's kind of nice. So I believe that I'll actually leave it here for right now. Thank you for your attention.